Alright, so after all that we learned, all that about concavity and absolute extrema and decreasing and increasing, we can finally do some curve sketching. And you can do it really any way you want, but this is the way that I've kind of just found that the book kind of does it, and other people kind of do it in this order. Maybe Mr. Stewart, I don't really remember how he did it in order. But I like to find the derivatives first, and then I like to find the critical points and the points of inflection, and I also like to look for any vertical asymptotes just so I can keep it in mind, and then I like to make the chart then. And then when I'm making the chart, then I'm looking at how each of the derivatives are acting at the points by just plugging them back in and seeing, and then I'll write them negative or minus, or if they're zeros. But quick reminder first that about x-intercepts and vertical asymptotes. X-intercepts, we're just talking about the x-intercepts with the original function. So we're just setting the original function to 0, and because when we graph, it'd be a good idea to have a solid graph that's on the x-intercepts. We won't put them in our chart, but they're a good idea to know where how the graph's where it's going. And vertical asymptotes are of the original function, and it's when there would be a 0 on the bottom. So if we had like 1x to the third over 2 minus x, or I mean, that's not x, it's a 3, 2 minus x, if this is at 2, then that when x is equal to 2, then this function would be at 0 on the bottom for the bottom half, and that's a vertical asymptote. So it's whenever there's a 0 on the bottom in a function. So we have to be aware of that too, so that we can draw that and understand what's happening. So our first one is number 14, and I believe this is section 6. So number 14, we get the function x plus 32 over x squared. So we find both the first derivative, second derivative, and there they are. So then we find the critical points, and we get x equals 4. So at x equals 4, there's a minimum or a maximum. We're not really sure yet. We're not going to do that just yet. We're going to wait until we put it in a chart. And then we do number, and then we find the possible point of inflections. But for this one, it's undefined. There does not have a 0. So there's no point of inflection. So it's probably just one large parabola. Could be a line. We don't know. I mean, it's probably not going to be a line, but, you know, we don't know. But it's not a weird, funky graph too much. Well, that we know of yet. So after we get those points, then we're going to be plugging them into the graph. So this is the general idea of the charts that we're making. We have a column for all the points that we found interesting, and we always start with a negative infinity, and we're talking about all the values up to the first point, then we'll talk about the point, then we'll go from the next point and the values from the next point to the point we just did to the next point, and then we'll talk about it at that point, and then from that point on to infinity. Then we have what happens at y, and we're usually only talking about it at the equal points, like x equals 4, not the values in between, because we're getting concrete values so that we're graphing it. Then the y column, or second derivative column, first and second derivative, and then we conclude what we see it's going on. After we mark the points in, we remember what we're doing. And I also marked all the x-intercepts here on the bottom. I found them. So from negative infinity to 0, we see that both the first and second derivative are positive. What does that tell us? Positive first derivative says it's increasing, and positive second derivative says it's concave up. So at x equals 0, though, it's the first function is undefined. I just put those at infinity because that's what they're just telling us. They're also undefined, but it just means that they're going way off, and it's all crazy right there. And then So then I wrote vertical asymptote because I already know from looking at the function x plus 32 over x squared that at 0 it will be a vertical asymptote. So I knew that from the beginning, but I'm just writing it now. And then from 0 to 4, we see that the first derivative is negative and the second derivative is positive. What does it tell us? It tells us it's decreasing now because its first derivative is negative, but it's concave up still. At x equals 4, first function is 6. It was a 0, and it's a relative minimum because second derivative is positive. And then from 4 on to infinity, we see that both the derivatives are positive, which shows us that it's increasing and still concave up. So when we take all these things into consideration, I like to dot my points that I'm going to be using. So I would have first dotted, what is this? This is the x-intercept, because I know that something's happening. I would have dotted my vertical asymptote, and my relative minimum that I found, I would have dotted at 4 and 4, 6. And then just what your goal is to just make a general sketch, and that's what I did. And it's always fun to see how close your general sketches are to graph. And looking at the how the calculator, graphing it, putting it in the calculator, it seems pretty close. So it makes me feel good. Sometimes it does not happen. Alright, so that was 14. Here's 18. So we get 2x squared minus 5x plus 5 over x minus 2. So we find the first and second derivative. Now, this one was a very tricky one, to be honest. After some queries with it, I finally figured just to put it in my calculator, and I just found out what the x-intercept, the critical points, and then for the second derivative, I figured out that it was undefined, so there's no point of inflections. And I also noticed that there's a vertical asymptote because if you plug 2 into the bottom, it'll give you a 0. But if you remember, and I didn't talk about it that much, but slant asymptotes. When we have a function where the degree of x on the top is larger just by 1 than the bottom, that it's going to be a slant asymptote. And I never told you exactly how we deal with those. How do we deal with them? We actually do long division. And so when I did long division, I just dividing the bottom into the top, and I got 2x minus 1 plus 3 over x squared minus 2. But that plus 3 over x minus 2 is the remainder. We're not worried about that. What I got here, that is a line, and that slant asymptote line is what the there's going to be a slight slant to the function at that line, so that neither of the lines on the graph are going to touch at that point. So that's also something that we have to take into consideration at the very end. So taking my points, I put them on here. A good way to just put the points on here is just to look for the smallest point and put it in the second one, skip 2, put the next one in, and skip 2, put the next one, and then these are just, you know, in between all those, from negative infinity up to that point, and then the point. So looking at what I plugging in values like at 0 or negative 1, I found out that the first derivative is positive, second is negative. That tells us that it's increasing but concave down. And at 0.775, first graph is negative 1, almost negative 2, but that second derivative was negative, so it's a relative max. And then in between that 0.7 and 2, both the second derivatives are negative, which shows it's decreasing and concave down. Then at 2, it's undefined. That's our vertical asymptote. We already know it is, so we don't really have to write much in there. I just wrote infinity because we know they're just going off all crazy. Then from 2 to 3.2, we get the first derivative is negative, second is positive, which tells us it's decreasing, but it's concave up. Then at x equals 3.2, we see that the first derivative is almost 7.8, and then both derivatives are positive, which shows that it's a relative minimum. And then at 3.2, we see that both the derivatives are positive, so it tells us it's increasing and concave up. And we also wrote my sine asymptote there, and then I drew it. First I drew my sine asymptote, it's kind of slanted too, and then I drew both the dots of my points, my relative maximum and relative minimum. Drew my slant asymptote, and then I just sketched it from there. And it's kind of a rough sketch, but that's still the point, that you're able to sketch it without having to plug everything into your calculator. And then for the last one, 29. 29, they give us y equals 3x to the fourth plus 4x to the third. First and second derivative first. Then I do my critical points. So I get x equals 0 and x equals -1. Then I get positive point of inflection, and that's x equals 0 and x equals -2/3. And then I check for vertical asymptotes. I don't have to worry because it's not a rational function, or it's not a fraction, so there's not going to be any vertical asymptotes, which is nice. So I have 4 points that I have to plug in here for possible occurrences. So, and 2 of the points were the same. X equals 0 for critical point and a point of inflection. So this graph's going to have something weird going on. We'll deal with it though. So at a value is less than -1, we see that it's decreasing but concave up. Then at x equals -1, we see its function is -1. It was a minimum because the second derivative is positive, values are bigger. Then values between -1 and -2/3, we see both are positive, which means it's increasing and concave up. At x equals -2/3, that's just a point along the graph. We see that it's just kind of a random point, but that it's a point of inflection because the second derivative is 0. And then we have -2/3 to x are between -2/3 and 0. And so we see that it's increasing but concave down. X equals 0. Everything's 0. It's kind of funny, but it's a point of inflection. It's also a point of so it would look like a relative minimum, kind of, but because it's a critical value or maximum, but it's a point of inflection just by the way that the graph is shaped, and that you see how you know that it's coming down at an angle, and you know it's going back up. So it's kind of another like little ledge that the graph does before it does something else. It just shoots off to infinity. And then when it goes off to infinity, both are increasing and they're concave up. And I do believe these are the x-intercepts. So I put in all my interesting points. I put in this intercept. I put in the relative minimum I found. I put in this -2/3 and -16/27, and then I put in 0, 0. So I know it's concave up, so I'm coming in from here and I'm just hitting all the points, and there's that weird point that it's all 0 and it's a point of inflection, and it kind of just sits there and then it goes off to infinity. But that is a graph, and I did it all without having to first plug it in and be like, okay, I'm just going to graph this first and then guesstimate. This is everything that you have to do, so I hope that helped.